Okay, so here goes the next one that we're actually going to have a video to go along with. Now again, the numbers are going to be a bit different from what's on the homework, but this is designed to give you a hand with solving it. Now this one's a multi-part problem. The first part says a tube is open on both ends to air, like the boom whackers from class. Conveniently enough, this is what I'm talking about, these are the boom whackers. And struck on a table. In this case, I'm going to go with hand instead. So this is the sound it's making. It's open on both ends, as you can see. No tricks. The lowest frequency tone that this guy is making is 495 hertz. Okay? Assume the speed of sound in air is 340 meters per second. So we're going to assume that our velocity of our sound wave is 340 meters per second. What is the length of the tube? Now, I could cheat and actually measure the length of this tube, but you all don't have the tube at home, so you're going to have to guess. Or we could use physics instead. Now, what I want you to remember is when we first started talking about this, the idea of nodes and antinodes. We used the standing waves that we generated, and you can remember back to when I was using the spring on the ground that was connected over here to a table. And we generated a standing wave with that, and I could make several different ones. I could make one that looked like this, where it was just one bump that would go back and forth like this, and then I had one where it was two bumps, second harmonic, where they'd go back and forth like this, and then we'd have three, and I might have been able to excite the fourth one, maybe even the fifth. Apparently I received something, but it all depends on how well I could get that frequency just right. But we talked about the importance of, we had a node over here, something that could not move. And then we had, on the exact opposite, an antinode that could move a whole lot. And that was the key to actually solving a lot of this. Now, with the tube that I have here, it's open on both sides, so my setup for my wave is that I have an antinode here and here, because it's open to air. It's free to move around all at once. And so, I know that I have antinodes here and here. And I want to know the frequency that I would get associated with that. The lowest frequency. Okay, so what I'm going to do is I'm going to do a drawing of a wave. This is kind of one complete wavelength. I start here, and then I end over here. And I've got, keeping track of it, I've got a node here, and a node here, and a node here. It's just like with the spring where we had the two, this was a full wavelength. These would go up and down, here are my antinodes, and I would have nodes on the ends and in the middle where they wouldn't move. However, I have antinodes here and here. Now the thing is, when this tube is open on both sides, I have antinodes in both locations, which means I need to match this up with two antinodes, right here, and here. And what's happened is, one antinode is here, and the other antinode is here, so I end up with one that looks a lot like this. Here's my wave. It's only a fraction of my wave, though, because I have an antinode here, and I have an antinode here, with a node somewhere in the middle here. At least, this should be associated with my lowest frequency. We'll talk a little bit about that when we get the chance. What I need to do now, so I know what my frequency is, and I know what my velocity is, so I can now find my wavelength. That's independent of the stuff that I've drawn here, but we're going to see how that too becomes important there. So I can find that my velocity equals my frequency times my wavelength, and we're going to plug in that 340 meters per second equals my frequency of 495 hertz. And I want to find my wavelength, very much like the other video that we did. Now, dividing both sides by 495, I find that my wavelength is, we'll do 340 divided by 495. My wavelength comes up to 0.687. Apparently 0.68686868 and so forth. I keep ending up with strange fractions. No matter. 0.687 meters. Now I will bring up something that you may have already thought of. 0.68, that's just shy of 70 centimeters or so. You're looking at a better part of 2 feet there. Probably not what this tube is. At least if you're paying attention to the numbers, you might think that. And that brings us back to up here. While that is our wavelength, which is the entire distance from here to here, the pipe isn't actually our full wavelength. That's why this drawing is important. We know that we're going from an antinode here to an antinode here. So, if I fit this in there, where those antinodes are, I can see that, okay, so I've got from here down to here. Well, this is a quarter of my wavelength, this is another quarter, here's 3/4, and here's the full wavelength. So if I go from antinode to antinode, that's actually half of my total wavelength. So in other words, my wavelength equals twice the length of that tube, right? Or the length of that tube, you could also look at it as the length of this tube is only half of my full wavelength. Both of them get me the same setup. I can say that my length equals my wavelength, over 2, not L. Okay. Both of these say the exact same thing. Okay, well we now know that my wavelength is 0.687 meters. That equals twice the length of the pipe. So I divide both sides by 2. And I find that L, we can see here that cancels out and I'm left with L equals my wavelength divided by 2, which was the other equation there. L equals, what's that going to come up to? 34-ish? 0.68 divided by 2. Yeah. So let me do 0.687 divided by 2 just so we're good on that. Okay, yeah. Equals 0.344 meters. In other words, I predict that this tube should be 34 and almost a half centimeters long. Let me double check that real quick. I have a meter stick. Hold it up here. Right now, I'm actually measuring it as about 32 and a half. My numbers are a little bit off. But I mentioned in the other video that I kept measuring the speed of sound in here as approximately 320 meters per second. Now, in reality, what that likely is it's probably an effect from some of my equipment that I end up a little bit off. But we can see here that we are very close, and there may be just a little bit of real-world situations that are throwing this off ever so slightly. But about 34 centimeters, we actually find this guy to be about 32 centimeters, but pretty close. And we can see how we actually apply this. You may be thinking, all right, but the numbers don't agree perfectly. That's all right. We have more parts to this problem. I then say, in part B, I now take the same tube and I cap one end, assuming that I can actually read and put a cap on at the same time. That's right, I did get a degree. Okay, so I've capped one end, making it closed on one side and open on the other. Okay? However, the length is unchanged. In this one, I might have changed the length ever so slightly by adding this in there, but probably not. The actual open space in the tube should be pretty much the same. And if I have changed it, it's by an incredibly small amount. I ask, predict what the lowest frequency the tube will make with this cap on the end. So now my tube looks something more like this. Now, thinking back to those nodes and those antinodes, I've got effectively a wall here. Now before, the air could go in and out freely, but now it's bumped up against a wall. In other words, it won't be able to move against that wall. And when something can't move, that's what we identify as a node. So I'm going to draw my wavelength again. I had nodes here, here, and here. And I had antinodes, or antinodes, here and here. Now, I've got a new setup. In this case, before we had an antinode here and an antinode here, so the smallest value that we could get is this. Now, we've got a node and an antinode. Well, the smallest value that has that is right here. Right? So I've got, here's a node and here's an antinode. So I'd end up with a drawing that looks like this. I have a node right here in the middle. Then I have it go up to an antinode over here. Where it is free to move, it's an antinode on the open end because the air can move in and out. It's not stuck, it can move about. On the capped end, the air can't move through the cap, so it's stuck there, making it a node. Well, in this case, my length of my pipe, which is still what we predicted with our actual numbers, we'll go with that, 0.344 meters. Now, our wavelength is actually very different because, as you can see, we've only got a quarter of one full wavelength. So now we know that 0.344 meters equals our wavelength over 4, because I've only got from here, this node, to this antinode. Okay, so I'm going to multiply both sides by 4. And I find that my new wavelength is going to be 0.344 times 4. My new wavelength is 1.3, let's call that 8 meters. Okay, well, we're still in my classroom where the speed of sound is still going to be 340 meters per second, and that will still be equal to my wavelength times my frequency. And we've now found our wavelength. We think 340 meters per second is going to be equal to 1.38 meters times our new frequency. I solve for my new frequency, and I find 340 divided by 1.38 equals 246.4 hertz. Okay. Measuring this a moment ago, and I'll try and set the camera up in just a moment so you can actually see these measurements, we ended up with 249 hertz is what I'm actually detecting for this sound. All right. Now there's one final question I have. Now we found the lowest frequency because we found one of the longest wavelengths, and we're going to see how that factors in just a moment, because now my question is, what's the next lowest frequency that this tube will make when struck with one end cap? Because from what we saw, there's one primary one that it makes, but it will also make some of the other standing waves that result in here as well. Okay, well for that, I know that I need, here's the capped end, still the same tube. I'm going to have yet another wavelength drawing here with antinodes here and nodes here. Now I know that I still have a node over here and I still have an antinode over here. We already found the smallest piece of this making the longest wavelength, where this was only a quarter of it. But if you notice, I've got from here to here. This is a node and this is an antinode. I can set that up, and I would end up with a drawing that looks like this. Here's my node. It goes up, goes back through the node, and then down here to an antinode at the very bottom, where I've got an antinode here. Now remember, the air is still free to move about in this tube. It's only fixed over here physically on the wall. Now when we set up this standing wave, this side is going to move a lot, and we're actually going to end up with yet another node in the middle, and an antinode over here. And now, this is my next wavelength. This should be my next lowest frequency. And so, what I'm going to do is, well, my speed is still 340 meters per second. I'm going to set that equal to lambda times my frequency. And now I need to find lambda, my wavelength. Okay, well, we know that we're looking at with this. This is the length of my tube, so the length of my tube equals 0.344 meters, and that also happens to equal, so if this is the shape of the wave that we have in there, I've got, this is 1/4, this is 1/2, this is 3/4, and then there's the full wavelength. This is actually equal to 3/4 my wavelength. Okay? Well, now I'll multiply both sides by 4/3, so I can get my wavelength. So I've got 0.344 times 4 divided by 3, and I end up with my new wavelength that I'm looking for is equal to 0.459 meters. Okay? So I'm going to plug that guy back in here and solve for my frequency. So I'll have 340 meters per second equals 0.459 meters times my frequency. I solve for my frequency and I end up with 340 divided by 0.459 equals 740.7 hertz. And I will try and set up so that you can see this. I've actually, the measurement that I was getting just a moment ago was 745 hertz is actually the second frequency that crops up. So I'm going to switch over the camera with the equipment so that you can actually hopefully see this. Alright, now what I have is I have the tube that we were using, the boom whacker, that we were using for our sample problem. So it's the one that we had measured out previously. And now I have it uncapped on both ends. Let's see what frequency we end up with. It's kind of hard to see there. I'm going to zoom in some. Maybe a little more. Looks right at about 479, 480 is what we're seeing on there. Let's see. A little off. Okay, so just shy of 500, but it looks like it's mostly centered around 480. 479, 484, those are numbers that I'm seeing in there. Okay, and now let's try it capped. That one appears to be 247. Okay, and then we also wanted to check for the next highest one, which happens right over here. It's right at about 742 is what I saw flash up there. So 740 range. I've got the reading pretty close, although it's probably slightly out of frame up here, that it's about 740, 737 or so. Okay, so that's actually, it's matching decently well. It's not perfectly what we found, but it's actually seeing the results right here.